We are going to start the lecture on advanced reaction engineering. So, multiplex reactors we will discuss. In our previous class we have discussed about the slurry reactors and different rates at different locations of that particular reactors that we have discussed, means gas absorptions, then diffusion, external diffusions from gas liquid interface to the bulk surface, and then from the bulk surface to the external surface of the catalyst particles, how reactants will move, and after that once the reactant molecule reach to the external surface of the catalyst, it would be diffused through these pores of the catalyst particles, and then it would be react inside of the reactor. So, individual rate we have discussed. So, how the absorptions, gas absorptions, this is the another diffusions, means interface to the bulk of the liquid diffusions, and then from the bulk surface to the external surface of the catalyst another diffusion is there. So, this is interface to the bulk the changes, and then bulk to the external surface of the catalyst, and then internal diffusion and reactions that will take place inside of this catalyst particles. So, here so many resistance are there, means driving force are there. So, that depends, means if we are able to control that way, then the efficiency of this particular slurry reactor performance we can improve or we can change, how we can change that. Okay. So, here so many way we can do that, means catalyst particle size we can change larger if we at the beginnings we have taken say particular shape or size of the particles. If we change that particular shape of the particles or size of the particles into the smaller particle, by that way we can control or eliminate the internal diffusion part, or if we put some stirrer inside of the reactor during these reactions or reactant component is passing through this reactor for the reactions, means if stirring is there, let us say, then that would help in the mixings. Mixing means mass transfer, means gas to the liquid or liquid to the surface of the solids, means that way the component transfer from one point to the another point would be easier. So, how that would affect, that we will basically discuss in this class. Okay. So, the different steps or 5 steps for that particular slurry reactors we have discussed, step 1, step 2, step 3, step 4, step 5, that part we have discussed in our previous class. So, once we have find out the rate of the individual points, and after that at steady state we have considered all rate would be the equals, and based on that these equations we have derived in your previous class. Ci, that is the interface concentration of component A, bubbles and liquids in that interface. So, interface concentrations if we know, rate of the reactions if we know, then Ci by, means from the experiment data we have to know Ci Ra value for the reactions, and corresponding mass of the catalyst 1 by m also we know, means let us say from the experiment if we conduct that initial concentration of the reactants a particular run once, let us say 2, 3. So, initial concentrations at this initial concentrations the rate we can find out, the amount of the catalyst was used, that we know. So, from here we can find out if we know m, 1 by m we can find out, and then if we know Ci and Ra, then Ci by Ra we can find out. So, then we have Ci by Ra and 1 by m we have for this particular systems, and for run 1 we have, similarly for run 2 also we will find out, similarly for run 3, run 4, run 5, the same experiment by changing mass of the catalyst, concentration of the component of the reactants, we can find out these are the components. Okay. So, once we know this table is ready, so then we can plot Ci by Ra versus 1 by m. 1 by m is the inverse of catalyst mass of the catalyst, the amount of the catalyst per unit, m is the units gram of the catalyst per dm³ of solution. Okay. So, how much quantity of the catalyst we have taken for this particular reaction, that we know. So, inverse of Ma if we plot this, then this line should be like this. Okay. So, with slope and intercept, the intercept indicate the gas absorption resistance, and the slope of these lines indicate diffusional resistance, that diffusional resistance plus reactions and at the same time external diffusional resistance. It is the sum of these two resistance RC and RR. So, these are the slopes, means if we are able to find out the slope, then total resistance due to this we can find out, and if we are able to find out the numerical value of RB, the gas absorption resistance we can find out. So, here this gas absorption part is this, here up to this is the gas absorptions. So, that also the absorption resistance depends upon the property of gas as well as the liquid. So, based on that resistance we can increase or decrease. So, if the gas absorption resistance is high, how we can lower that gas absorption resistance, means once resistance is lower, then more and more gaseous component will be absorbed in the liquids, then more and more gaseous component will take part in the reaction. Similarly, for if you are able to decrease this resistance, means external diffusion resistance, so then rate of transfer of mass from the gas to the liquids and to the external surface of the catalyst would be very fast. Similarly, if very fast the reactor molecules come inside of the pore of the catalyst, then easily reactions will be take place. Okay. So, here you can see this RB part, absorption resistance, that is independent of the catalyst amount that you have taken. Okay. So, here these two components, means absorption resistance and diffusional resistance, that part we are writing this way, means RB by RCR into 1 by m, that is the intercept and slope multiplied with mass of the catalyst that was taken per DMQ solution or volume of the solution that was taken for that particular reactions. So, here you can see if we write this RB equals to RB remain the same and RCR C, and 1 by m we are putting m into at the top, and then RB we can write RB equals to this 1 by KB into AB, and that, and at the bottom or denominator we can write 1 by RCR equals to, I said, RC plus RR. So, RC equals to this 1 by Kc into AC and RR equals to 1 by eta K. So, here two components are there, external diffusion resistance and internal diffusion resistance plus reaction. This is for internal diffusion and reactions, this is external diffusion and resistance, and this is for absorption resistance. So, if we change the quantity of the mass of the catalyst for that particular reactions, if quantity of m if we decrease, then the combined resistance will decrease. Okay. This if the amount of the catalyst at the beginning was taken high. So, if you decrease that quantity, so then combined resistance also will decrease. So, here it indicate Kc and eta, that will be increased. Okay. So, Kc is the that constant for external diffusion mass transfer coefficient, and eta is the that efficiency, means if particles this part, means if we want to make it balanced, so then this part we have to increase Kc or eta value we have to increase. So, combined resistance will decrease by decreasing the slope. Okay. So, if we take the decrease the catalyst quantity, then combined resistance will decrease, and as a result decreasing the slope of the systems. Okay. That is means we can that way we can control the resistance of individual components. Okay. Means external diffusion resistance, internal diffusion resistance, that how we can control that. So, now next step is to learn, means how we can separate RCRR by external diffusion resistance, internal diffusion resistance controlling, and surface reaction is controlling by changing catalyst particle size. Okay. So, catalyst quantity we can change, means a large quantity for that particular reaction, small quantity of amount of the catalyst that we can take for that particular reaction, or we can change, I said that if we change particle size, that is also one of the parameter to control the diffusional resistance. Okay. So, that how that would affect or how we can control that. So, that we will discuss. So, here basically means if diffusion resistance is controlled, means I said gas absorptions may be controls or maybe diffusion may be controlled. See here, see in this graph of slope we here said this is another resistance, that is the gas phase absorption resistance, and this is diffusional resistance, two resistance are there. So, if we first case 1, if we assume that diffusion control, means the systems we have there diffusion of one component from one point to the another point, that affects or controls overall the reactions. So, then how we can control the reactions? By controlling that diffusional part. Okay. So, for that we have to decrease the particle size, or we have to use more amount of the catalyst. So, how that we will discuss. So, this diffusion basically internal and external diffusions. Let us say if we change, let us say initially we have a larger size of the particles. So, the catalyst particle size, let us say 10 kg of the particles we are using for a particular reactions, and catalyst particle size was this, that is the particular diameter of size of the particles was there. If the same quantity of the catalyst if we take, but the catalyst particle size would be decreased, means smaller particle size if we considered, means particles diameters may be dp3, let us say this dp2, and this is diameter of the particle dp1. So, particle size or diameter we gradually decrease this way. So, if we decrease the particle size, but remain the same quantity of the catalyst, then so what would happen? The slope that would decrease this way. Okay. So, the slope is the resistance basically particular, that diffusional resistance. So, diffusional resistance how you can control, or we can decrease by decreasing the particle diameter. So, that way, but absorptions, gas absorptions we cannot control, that is the for the systems, that is the remain constant, but by changing the particle diameter we can decrease the slope. Okay. Decreasing the slope and decreasing the particle size, if you decrease the particle size, the slope of that lines will decrease. Therefore, the overall resistance due to the diffusional resistance that we can control. Okay. As the particle size decrease, what would happens? Eta value and Kc value both will affect. So, eta and Kc value both will increased. Okay. If we decrease the particle size, effectiveness factors eta that will increase, and Kc that is the mass transfer coefficient, that is also increased. So, here see means that way particle size we are decreasing this way, and gas absorptions if we use more catalyst. Okay. So, if we use more catalyst, what would happen? Here's low absorptions in this case, see here the resistance was this, and if we use more catalyst, the absorptions intercept is this. The diffusional resistance remain the same, but the absorptions resistance we can decrease. Decreasing the gas absorption resistance is good, actually decreasing gas absorption resistance is good. So, here initially gas absorption resistance was this, and if you use more amount of the catalyst, so gas absorption resistance would be low. Okay. So, this way this part also we can control by using more amount of the catalyst for that systems. Okay. And next step is the here we have discussed the diffusion controls. If gas absorption part is controlled, in this case diffusion was controlled, and in this case now we will discuss about the gas absorption phase is the controlling steps. Okay. So, in this case here see this Ci by Ra and against 1 by Ma if we plot, then there is a intercept would come, and then these lines will be like this. Okay. So, here's you can see high absorptions and low resistance, and here intercept gas phase absorptions interface is large. Okay. The slope is small in this case. So, here's this part you have to reduce. Okay. Means here's the gas absorption that is very high, gas absorption resistance is very high. So, if we want to get more and more gas would be get absorbed over the surface means in the liquids. So, then this part you have to reduce. So, how that we can control, means if the gas absorption is the controlling for this particular system, and if we decrease the gas absorption resistance, means here it was this, if we want to reduce that, then for that what we have to do, we have to produce more and more bubbles, means through this part at the beginning we have discussed that here is the sparger is there, gas is coming entering here, bubble formation, gas bubble formation is there. So, what we have to do, the sparger diameter we have to reduce, then we can increase the more and more gas bubble diameter we can change. Okay. If sparger diameter is reduced, then gas bubble diameter will decrease. So, then more and more gas will be absorbed in the systems. At the same times smaller bubble diameter of that bubble that will forms in the liquids, that would be smaller diameter, and more bubble formations would be there. So, by that way the gas absorption resistance for that systems we can decrease. Okay. So, another one is the diffusion reaction controls using stirring also. So, if you use more catalyst, then also using more catalyst we can gas absorptions, that also part also will increase, means absorptions, if it is increased then absorption resistance will decrease. So, here see here if it is like this, here resistance large slope is there, here intercept is very small. So, if we use more catalyst, so then absorption should be more. Okay. So, then the here intercept or resistance was high, here intercept was very low for gas absorptions. So, in this way means how we can increase that. So, inside of the reactors, if we stirring that liquid, gas and solid material is there inside of the reaction systems or reactors, if we use the stirring or stirrer, then external resistance will decrease. So, by that way diffusion reactions we can control. Okay. So, here now we will discuss about the catalyst particle size. Okay. If we vary the catalyst particle size, so how that would means changes overall the diffusional resistance. So, let us say we have a large size of the particles, very small size of the particles. So, here this is the combined resistance, external diffusional resistance as well as internal resistance is there, okay, and reaction. So, let us say if we take very small particles is there, and in this case surface reaction means surface reaction is limited, means surface reaction, that is the control the reactions, and in that case this combined resistance we can write this way. Okay. So, here see 1 by Kc Ac, that is the close to 0, and eta is going to 1, close to 1, means when if we can means uses very small particles or very small size of the particles instead of a large size of particles. So, what would affect, then effectiveness factor would increase, this eta value gradually will increase and that would reach to the close to the 1. So, if we use large size of the particles, that eta value would be less than that, let us say 0.6 it was there. So, if we decrease or means here large size of the particle was there, if we decrease the particle size into smaller into, then effectiveness factor will increase. So, effectiveness factor will close to increase close to 1. So, if we take smaller particles for our systems for the slurry phase reactor, then in this combined resistance this part would be close to 0 and this eta part would be 1, then combined resistance would be like this, RCR equals to 1 by K. So, if we particle diameter becomes small, surface reactions controls and the effectiveness factors affect to effectiveness factor approach to 1. Okay. So, then the combined resistance, external diffusion resistance and internal diffusion resistance as well as reactions, that would be like this. Okay. RCR equals to 1 by K, that is the reactions rate constant, that would inversely related. Okay. So, here these equations we can write this way also, RCR, that is the combined resistance 1 by K dP to the power 0. Here dP, there was no dP is the diameter of the particles, means I said that is the dP is the diameter of the particles, that powers 0 means 1, dP 0, that means 1. So, nothing is there. So, just we are to get it more easy to what actually I am to mean. So, therefore, dP, if we consider dP equals to 0, so then after taking ln's left hand side and right hand side, left hand side ln CR we can plot and right hand side ln dP we can plot. Okay. So, here you can see the slope would be 0. Okay. So, this is the RCR, RCR should be actually this way, but here it is coming 0. So, it is independent of particle size, means surface reactions when particle size is smaller, then surface reactions will control effectiveness factor, that is reached to the 1. So, that part we will discuss in our another class about this diagram or figures, how diffusion and diffusion and reactions affect with the particle size or diameter and Theli modulus, that part we will discuss, already have studied also I think. So, if it is observed that RCR, that is the total resistance independent of the particle size. For very small size of the particles, the slope equals to 0, the surface reactions rate is independent of the particle size. So, under these conditions, the surface reactions is independent of the particle size, surface reactions rate is independent of the particle size. Okay. So, here in this case the lines would be like this. If we increase or decrease of the particle size, under these conditions there is no diffusional resistance. Did you get my point? So, here actually how the particle size means, if we vary the particle size, individual resistance, that how that would affect. Okay. So, from the beginning for the reactions, if we take smaller particle size, then the total diffusional resistance independent of the total resistance independent of the particle size. Okay. So, slope equals to 0. Similarly, in next case, if we instead of taking small size particles, some little bit larger or bigger size of the particles we are considering, small to the moderate size of the particles. So, then some internal diffusions would be there, okay, or internal diffusions remains inside of the particles, and that would related with the particle diameter. So, this type of correlations is there for if internal diffusion is there for any spherical particle system. So, effectiveness factors and particle diameter is like this. We can read these equations later. So, there is another chapters we will study that. So, now eta and diameter of the particles, how they are related, that is inversely related. Effectiveness factor, eta is the effectiveness factor and dp is the diameter of the particles that you have taken. So, in these equations, that is the R, that is the internal diffusion and reactions rate, that is the resistance equals to 1 by eta k. If you substitute eta equals to this part and rest of the parts constant, these are the parts constant. So, alpha 1s, that is the constant part, R that directly proportional to the dp to the power 1s. Okay. So, this equals to come. So, or RR we can write alpha 1 into dp, okay, dp 1. So, here if we take ln left hand side and right hand side, and after that if we plot by changing particle size, so then the slope would be like this. Okay. So, internal resistance, reactions and diffusions both are controls, and internal diffusion is exist. In that case, we have taken moderate size of the particle instead of smaller size of the particles. In that case, the slope would be 1. Okay. So, here's internal the resistance, combined resistance, that will vary linearly with the particle size. See, here's resistance RR, that is the resistance due to the reactions, that is directly proportional to the particle diameters. And earlier case, when small size of the particles you have taken dp to the power 0, here slope equals to 0 and here slope equals to 1. Okay. Here slope equals to 1. So, here's when moderate size of the particles you have taken, so that internal diffusion exists, and then we can say that the particle diameter, if we increase or decrease, the overall resistance due to the diffusion, that would affect, mean that would change. Okay. That is diameter particle size, that is linearly related. Okay. Then the overall rate of reactions can be increased by decreasing the particle size. So, here if it is linearly increased, so then if you decrease the particle size, then this resistance will decrease. Okay. So, in case of the moderate size of the particles at the beginnings, if we have taken for this particular reactions, if we decrease the particle size, then the total resistance we can decrease. Okay. So, similarly, in the case 3, moderate to large size of the particles, initially that was taken very small size of the particle for the reactions, later moderate size of the particles, now we are considering moderate to the large size of the particles. Okay. In that case, what would happen, that we will see. So, here when moderate large size of the particles you have taken, then external diffusions part is very important, external diffusion resistance part is very important. So, then this RC equals to 1 by Kc AC, that we have discussed. So, here AC equals to, we can write 6 by dP and rho p. AC means external surface area of the catalyst particles. So, that is the particle surface external surface area per unit mass basis 6 by dP rho p. If you know the diameter of the particles and density of the particles, then AC you can find out. So, now Kc is what is Kc? Kc is the mass transfer resistance or mass transfer coefficient. Okay, Kc is the mass transfer coefficient. Here two components are there, AC and Kc. AC we can find out by this way, catalyst particle diameter and density we can find out, and Kc part, that is the mass transfer coefficient. Since gas and large or bigger size of the particle is there, so then external diffusion should be there. So, for that we have to consider Serud number. So, how Serud number and mass transfer coefficient is related, for that this part there are two cases we are consider. Okay. So, here we are going to discuss Kc part. Kc is the mass transfer coefficient. Okay. So, mass transfer coefficient how we can get from the experiment. So, here means suppose we have a system is a batch reactors and their fluid is stagnant. Once the fluid is stagnant, solid particle is there, then fluid come in contact with the surface of the solids and then mass transfer will take place, particles and fluids. So, in that case there is no shear stress. Okay. Small particles moves with the fluid motion such that there is no shear between the particles and the fluid. That implies diffusion of the particles in the stagnant fluid. Fluid is the stagnant, means we have taken a batch reactor. Here case 1 we are discussing, means in a batch system there is no flow, and another one case 2 that we will discuss when there is a flow system, means particle is there, liquid is also moving. Okay. In that case shear stress would be there, in between shear stress, and here when it is the stagnant fluid is there. So, in that case there is no shear stress. Okay. Then Serud number we can write Kc dP by dAB equals to 2. Okay. So, these correlations I think in mass transfer you have studied. So, here Kc equals to 2, we can rearrange this equation, Kc equals to 2 dAB by dP. Okay. dP is the diameter of the particles and dAB, that is the diffusivity of component A and B. Okay. Binary mixture is there, so binary mixtures, in that case the diffusivity dAB, let us say here if we consider hydrogen and some unsaturated liquids is taken. So, then in that case the diffusions we have to, diffusivity we should know, that we can put it here, then Kc value we can find out if you know dP. Okay. So, now this Kc and AC we are substituting here in this equation. So, then Rc we can write this, Rc equals to, if we substitute AC and Kc here in this equations, then this equation should become this, some constant alpha 2 some constant dP square. Okay. After that if we take log, okay, these equations if you take log and if we plot RCR versus dP, then external diffusion, since we have taken large size of the particles, moderate to large size of the particles, in that case the slope would be 2, this here ln RC ln alpha 2 plus 2 into ln dP, that would come. So, ln RC and ln dP if we plot, the ratio would be the slope, this is the intercept part, and then slope equals to ln RC by ln dP, that would be 2. Okay. How that is coming 2? Then the slope would be the 2. When external diffusion resistance is there, external resistance to diffusion is there, and if we plot, here we have taken RCR, RC and here RCR, this is the combined resistance, means in combined resistance both are there, RR and RC. So, RC part is varying with the particle diameter, RR part remain constant, then overall RCR part will affect, since RC part is affecting with the particle diameter, therefore, RCR part would affect. Okay. So, if we plot them, then these lines would be like this and the slope of these lines is 2. Okay. So, in these 3 cases we have considered this. Now, here the fluid was stagnant, in that case Serud number and mass transfer coefficient we have considered this. If the system is not stagnant fluids, means there is flow is there. Then Sherwood number we have to consider some correlations, these correlations, this is the case 2, here fluid under motion, okay, means inside of the reactor liquid is there, solid catalyst particle is there, gas is flowing. Here liquid was earlier was case 1 stagnant, here if we consider liquid is also flowing, flow systems, in that case first link correlations you have to consider for Sherwood numbers. So, in the first link correlations Sherwood number and Reynolds number, Smith number, how they are related, this type of equations you have studied. So, Sherwood number directly proportional to the Reynolds number to the power half, Sherwood number equals to Kc dP by dAB we know, and Reynolds number equals to dP u by nu, that we know. Okay. Then from here we can write Kc equals to dP to the power, here is dP to the power half, here is dP. So, we can write dP to the power half, okay. Kc inversely proportional to the dP to the power half, and from AC we know this. Now, Kc and AC equals to this, okay. So, if we take this, or Kc equals to Rc equals to, if we inversely if we take this Rc equals to 1 by Kc into AC. So, if we substitute this, then Rc equals to alpha 3 some constant dP to the power 1.5, dP to the power 1.5, how they are coming this, okay. So, Rc equals to 1 by Kcac, here Kcac we are substituting here. So, then this equation should be this. If we take ln Rcr equals to some constant alpha ln alpha 3 plus 1.5 ln dP. So, if we plot this ln dP versus ln Rcr, then the lines would be like this and slope would be 1.5 in this case, okay. So, slope would be 1.5. So, in this case means when there is a liquid that is under flow or liquid is under motions, in that case Sherwood number is these equations, we have to consider in this case Kcac that is inversely proportional to the 1.5 to the power of dP, and then Rc equals to this, and from here we can write, and here slope equals to 1.5. So, now in these 3 cases we have considered since when particle is very small particles, in that case that resistance due to the diffusional resistance, particle size, diameter, how they are related, slope equals to 0, surface reaction is limited in that case. When RCR moderate size of the particle, small to moderate size you have taken, then slope equals to 1, okay. And when large size of the particles, here small size of the particles you have taken, here moderate size of, here bigger size of the particles you have taken, in that case the resistance RCR, that is the diffusional resistance, that may be external, internal and reactions resistance and particle diameter, how they are related, this is this, okay. So, large size of the particle is this 1.5 to 2. So, if it is stagnant fluids then 2, if it is flowing liquids then 1.5, and this is for 1 moderate size of the particles or very small size of the particles, the total resistance independent of the particle size. So, all these 3 equations if we plot together, okay. So, plot together, so then ln RCR against dP if we plot, then if slope equals to 0, if we plot RCR against dP, if we get slope equals to 0, the lines will come, okay, based on the experimental results. If the lines will come, that is horizontal, slope equals to 0, then we can set reaction is limited, okay, the reactions is controlling. If nature is coming like this, okay, RCR against dP, if it is coming like this, we can say slope equals to 1 and internal diffusion is limited under this case, okay. If RCR against dP if we plot and the slope is coming like this 1.5 to 2, slope equals to for this line, then we can say external diffusion resistance is limited, means external diffusion means bulk liquid to the external surface of the catalyst, the mass transfer that is limited for this particular system, and one this type of experimental result is coming and we are getting from the slope. From here we can see which one is controlling, external diffusion resistance is controlling, internal diffusion or surface reaction is controlling. Okay. So, surface reactions would control under this case, internal diffusion will control under this case, and external diffusions resistance that would control under this case. Okay. So, these three way means we have to plot the resistance against the particle diameter, and once we know which is the controlling means which particular resistance is controlling for our system, then accordingly we can increase, either increase or decrease the particle size or increase the stirring rate of the inside of the reactors. Gas, liquid, solid is there, stirring means stirrer would be there, stirring speed either increase or decrease, that also we can do, okay, depending upon the situations what we are dealing with. Okay. So, I think how resistance means which particular means external, internal or surface reaction, which one is controlling, this is the total resistance. So, this part for the reactions and this part for resistance for external diffusions. Okay. So, now this part is okay. I think how the particle size or particle diameters is affect in case of the total resistance for a slurry reactor or multi-phase reactions when we are dealing with gas, liquid and solid system. So, depending upon that, so we can control say particular system. So, based on the experimental results. Okay. So, I think it is clear. So, in our next class or next day we will discuss some numerical problem means based on this. So, how much catalyst we should take for a particular system, whether catalyst quantity will increase or decrease for resist or eliminate that particular resistance for the systems. Okay. So, today is up to this, I think it is clear to you. Okay. Thank you.